I saw some problems of CSAT real problems, and in this video we want to work on the ideas that were used in those problems. But the problems we want to solve have been chosen from sample problems of CSAT with same ideas of real problem, and also from other exams like AMC and other parts. For example, this problem is from AMC, and the ideas are what? If you consider the ideas concerning small example, which is useful in sample problems of system and real problems that I saw, composition of functions, telescoping rules on product, ideas for finding closed form of a recursive sequence, ideas in game strategies, backward induction, invariant in strings. This one was useful in real problem of CSAT, in sample problems of CSAT, in SUMAC, Stanford summer camp, and also many other exams, probably in dice game. Okay, so let's start. If you want to learn other ideas that were used in real problems of CSAT, you can send message to my WhatsApp number in the description comments. Okay, so let's start with first one. Okay, so in this problem, we want to see backward induction means what, ideas for finding closed form are what, telescoping rules, sum product is what. Ideas for finding closed form in one problem of also BMO, last BMO1, BMO1 2022 was useful. Let me tell you there are what. Incation language has the following two rules. B is a word. If X is a word, then X is a word. A. Give an expression for the number of B's in a valid word. Okay, so we know B is a word, and then here, if X is a word, here our X is B. B. So 6 B's is a word. 4, 5, 6, 2, 4, 5, 6. Now, our X is this. So here we can write 3B's, and then we can write 6B's, again 6B's, and again 6B's. So how many B's are there? 21. So how many B's are there here? 6. And now we want to see how we can find the form. Look, it says if X is a word, X is a word. So if it has K words, we want to see how many words does it have. If the length or let's say number of B's equal here K, we want to see how many do we have. 1, 2, 3, 3. Here K, 3K. So from K we can conclude 3K. So 3 plus 3K. So from 1 we can conclude 3 plus 3, 6. From 6 we can conclude 3 plus 18, 21. From this one we can conclude 3 times 21, 63 plus 3, 66, and so on. Okay? Now it says give an expression. So one way is like this, but we can say, for example, like recursive sequence, we can say an. If it is, for example, an, it is an minus 1. The recursive sequence is an equal to 3an minus 1 plus 3. For n is at least 2, and a1 is 1. Okay, now I want to show you how to find closed form when we have a constant coefficient, like 3. And also we have another thing when we have like this, an equal to an minus 1, for example, plus n minus 2 factorial, a1 is 1. So try to find also closed form of these as homework. When we have, look, the coefficient here is not constant, it's n, but here is constant. I will tell you the strategy for finding closed form of this recursive sequence. Closed form means what? For example, an equal to n squared, or n squared plus n, something like this. We call it closed form, but this form is recursive sequence. Why? Because for finding an, we need an minus 1. For finding an minus 1, we need an minus 2, and so on. But here, for finding an, we only replace n here in the formula. So let's see how we can find closed form of an. Okay, for this problem, we see this coefficient and we define a new recursive sequence, which is an over 3 to the n. Okay, now we divide this equation by 3 to the n. So it will be an over 3 to the n equal to 3an minus 1 over 3 to the n plus 3 over 3 to the n, which is an minus 1 over 3 to the n minus 1 plus 1 over 3 to the n minus 1. An over 3 to the n is bn. An minus 1 over 3 to the n minus 1 by definition of bn is bn minus 1 plus 1 over 3 to the n minus 1. So we can conclude bn minus 1 equal to 1 over 3 to the n minus 1. If we decrease n, bn minus 1, the rest is similar to classic telescoping rule. It's 1 over 3n minus 2. And we write bn minus 2 minus bn minus 3 equal to 1 over 3 to the n minus 3. And so on up to b2 minus b1 equal to 1 over 3. And if you add all these terms, it will be bn minus b1. a1, b1 is what? Is a1 over 3. a1 is what? Is 1. It's 1 over 3. So it will be what? It will be 1 over 3. This one, b1 is 1 over 3. And if you add all these terms, it will be 1 over 3 plus 1 over 3 squared plus 1 over 3 to the n minus 1. And let me tell you an identity that you should memorize. There are around 5 identities that you should memorize. One of them, hockey stick identity, and so on. Again, if you want to learn them, as I said before, feel free to send a message. My WhatsApp number in the description comments. Okay. It is this. So Pn equal to what? 1 over 3 here. Plus for this part, I factor from 1 over 3. It will be 1 plus 1 over 3 plus 1 over 3 to the n minus 2. And it is equal to 1/3 plus 1/3 times, here we use this formula. It will be 1 minus 1 over 3 to the n minus 1, 1 minus 1 over 3. And if you calculate that, it will be 1 over 3 plus 1 over 3. 3 and 3 here will be cancelled. So 3 minus 1, 2. It will be 1/2 times 1 minus 1, 3 and minus 1. Now, it is what? It is Bn. Here we said. An is what by definition of An? An equal to Bn times 3 to the n. Bn times 3 to the n. So if you multiply 3 to the n here, it will be 3 to the n minus 1 plus 1/2 times 3 to the n minus 3. Okay, let's check to make sure our formula is this. A1 should be 1, it will be 3 to the 0 plus 1/2, 3 minus 3, which is 1 is correct. A2 is 3 to the 1 plus 1/2, 3 squared minus 3. 9 minus 3, 6 over 2, 3, 3 plus 3, 6, exactly. A3 is 3 squared plus 1/2, 3 cubed minus 3. 27 minus 3, 24 over 2, 12. 9 plus 12, which is 21. And are exactly the things we've calculated here. 21. Next one, 66. Also, you can check next one. But most of the time when you check these three, it will be okay. If you check A4, it will be 3 cubed, which is 27, plus 1/2. 3 to the 4th, 81, minus 3, 78. 78 over 2, which is 39. 39 plus this is 6, 66. Okay, so our answer is this, and we've solved part A by using a way for telescoping rule, sum product, and finding closed form. Part A was finished. So let's focus on part B. It says suggest a third rule such that all multiples of 3b's are valid word, and the only other valid word is a single b. Okay, we found in previous part that an equal to 3an minus 1 plus 3. an equal to 3, an minus 1 plus 3, and a1 is 1. And obviously, a1 is less than a3, a2 less than a3, and so on. It is increasing integer sequence. Now, an is number of bits in nth letter. Now, here they were what? They were 1. They were 3 times 6, 3 times 21, 66, and it says what? All multiple of 3b's, we want to be good. So here the only condition you can add is if x is a word, then x is a word. Okay, like the conditions here we have. B is a word. If x is a word, then this is a word. If this one is a word, we can write then x is a word. By this definition, we can conclude what? If we have, for example, if we have k, the length of this is k, the length of this is k minus 3. Now, all multiples of 3 are good. Why? Because from a2, all of them are multiple of 3, 621, and increasing function. So if you consider any multiple of 3, like what? For example, like 27. Because 66 is good, because a1, a2, a3, from a2, there are multiples of 3 and go to infinity. So there exists ai that is greater than 27. For example, here 66. And because of third rule, 63 is a word, 60 is a word, and so on, we reach 27. So in general, if, for example, you have 3q, there exists ai which is greater than that, then ai minus 3, and so on to reach this. We have exactly the same thing in backward induction, and we can solve some problems. It is not so much typical like forward induction, but in some problems of IMO and other exams, backward induction useful if you want to solve more problem from backward induction. As I said before, feel free to send message my WhatsApp number in the description comments. Okay, part B we've solved. Part C, replace third rule with rule 3 with the following this. If x is a word, then x is a word. It means if the length here is 1, 2, 3, 4, 5. If k is, we erase 4b, so k minus 4 is a word. Find all parts pq such that for all integers n greater than equals 0, the expression pn plus q gives the length of all valid words. Okay, here let's use a small example. We know from first part b is a word from first rule, so length 1 is okay. From here, we know that k to 3k plus 3 was okay. Also from this part, k to k minus 4 is okay. So from 1, we reach 3 plus 3 is 6 by using this 6 minus 4, 2. So we have 1, 2, 6. Now, if we use 2 here, 3 times 2, 6 plus 3, 9 is okay. And 9 minus 4 is 5, okay. 5 minus 4, 1 is okay. So let's arrange them again. 1, 2, 5, 6, 9. Now for 5, we can say that 3 times 5, 15 plus 3, 18, okay. 18 minus 4, 14 is okay. 14 minus 4, 10 is okay. 10 minus 4, 6 is okay. So we've applied 5, so it will be 1, 2, 5, 6, 9, 10, 14, 18. Let's apply it for 6. For 6, we have 3 times 6, 18 plus 3, 21. 21 minus 4, 17, okay. 17 minus 4, 13, okay. 13 minus 4, 9 is okay. And the rest will be here. Let's arrange them again. 1, 2, 5, 6, 9, 10, 13, 14, 17, 18, 21. So if you consider the numbers, we will see, okay, 5, 6, 9, 10. What are the relationship? Because we subtract by 4, k minus 4. The remainder when divided by 4 is important. Why? Because look, when we find 21, for example, It is 4k plus 1. We see 17, 13, all 4k plus 1s. And 9, 5, and 1s. Probably we guess that. Here, as you can see, we are working on some small example and we want to generalize the idea. So we will see and we guess that if we can find a large 4k plus 1, 4q plus 1, then because we can subtract by 4, we can cover all numbers. Then when divided by 4 is 1. Now, if we consider 18, it is 4k plus 2. It is 4k plus 2, 4k plus 2, 4k plus 2, 4k plus 2. So we guess that 4k plus 1 and 4k plus 2 are okay, but other numbers are not. It says what? So it says find all pairs PQ such that for all integers n greater than equals 0, the expression this gives the length of all variables. Okay, so I found 4q plus 1 and 4q, for example, plus because I don't want to use these things, let's say, for example, 4r plus 1 and 4r plus 2. So it says, and here r is at least what? R is at least 0. Here also r is at least 0. So if you write Pn plus q, which n is at least 0, p is 4, q is 1, p is 4, q is 2. So our PQs are what? Are 4, 1 and 4, 2. Okay, we found these two things. Now we should prove. At first, we should prove that why we can see all 4n plus 1 and 4n plus 2, and why we cannot see 4n plus 3 and 4n plus 4. So let's prove it. At first, I want to prove, let's call this one, for example, lemma 1. 4n plus 2 and 4n plus 3 are not in our sequence. How we can prove it? At first, we have 1, okay, and we have two actions. As I said, k to 3k plus 3 here by our rules, and k to k minus 4, okay? So the first one is 1. Now, we know by this action mod 4 won't change, okay? K and k minus 4 mod 4 are equal, so we don't use that. So we focus on only k to 3k plus 3. If k is 1 mod 4, then 3k plus 3 will be what? Will be 3 plus 3 if we replace k with 1, which will be 6, and 6 mod 4 is 2. Okay? So from 1 we can go to 2. If k is 2 mod 4, then 3k plus 3 mod 4 is what? 3 times 2, 6 plus 3, 9. If you replace k with 2, and 9 is 1. So here we understand what? If a number, the remainder is 1, and we use this rule, it goes to 2, and if we use for 2, it goes to 1. Again, 1 to 2, 2 to 1, and if we use this one, it won't change. Okay, so we've proved the first one, and now we want to prove second part. That why all 4n plus 1 and 4n plus 2, we can reach all of them. Okay, lemma 2. Lemma 2 is what? We want to prove all 4n plus 1 and 4n plus 2, which n is greater than 0, are in our sequence. So how can we prove it? So solution. We know 1 is in our sequence, and from k, you have 3k plus 3, and k minus 4 will be okay. So the only thing you need to prove is that for any 4n plus 1 and 4n plus 2, you can find a greater one with same remainder when divided by 4, then by k to k minus 4, you can reach. Let me tell you why. So a1 is 1. We want to use this, okay, first. a2 is what? Is 6. a3 is what? Is 21. a4 is what? 66. And if you consider mod for these numbers, it is 1, it is 2, it is 1, it is 2. And here in lemma 1, we proved you can rewrite the same thing. If k is 1, 3k plus 3 is 2. 1 goes to 2, 2 goes to 1. goes to 2 and 2 goes to 1. And obviously we know that a1 is less than a2, it goes to infinity. So any number, for example, suppose x, which is, for example, 3t plus, for example, 3t plus 1. We can find ai that is greater than this. And then by this rule, ai mod 4 is, why I've written 3t plus 1, 4t plus 1. The remainder when divided by 4, for example, is 1. So you subtract by 4, minus 4, minus 4, and you reach this. If the remainder of this is 1, then we can reach. And because alternatively it is 1, 2, 1, 2, and it goes to infinity, we can do that. For t plus 2 also, you can find aj such that the remainder when divided by 4 is 2. And if you subtract by 4, it reaches this one. Okay, so it was similar to backward induction. So we proved this problem completely. Okay, and we have also similar problem in strings. We will solve in, let me tell you, as homework, you can solve SUMAC 2022. It is for Stanford math tournament. There are lots of problems in strings in that exam, 2022, 2023, similar problems that you, in some part, you should create like this. And also here invariant, for example, mod 4 should be 1 or 2. In next part also, we use invariant in a string. Again, you can use same SUMAC problem, Stanford Summer Camp 2022-2023. If you wanted more homeworks or wanted the solutions of other exams, CSAT, as I said before, feel free to send message to my WhatsApp number in the description comments. Invariant in strings, problem 8, sample problem with this idea. So the problems was useful also in real CSAT. A whiteboard has PA symbols and MB symbols written on it. You choose any two symbols to erase and replace them with another one according to the following rules. AA to B, ABBA to A, BB to B. If you continue to apply replacement for as long as possible, which values of P and M result in a single A remaining at the end. Okay, we want to reach in a single A. So let's consider first let me write the number of A equal to P, the problem says, from assumption number of B equal to M. We want to reach to a single A remaining at the end. Okay, so if we have one A, it is okay. So if it is 1, 0, it will be okay. AA is not okay, we reach B. AB is okay, so AB is what? 1A, 1B. And BB not okay because we reach B. Now, consider three letters. When we have three letters, we have AAA, AAB, A. After this, we try to generalize. ABA, BAA, when we have one B. When we have two Bs, ABB, BAB, and BBA. And when we have three Bs, 3B. Okay, for this one, 2A goes to B, BA, and BA goes to A. So A3B0, it will be okay. And we want to see it is not related to the arrangement. Let's check AAB, BBB. Also, we can say AB, AAB. Okay, we will see. Okay, if you check the others, they won't reach. ABB, BB goes to B, and AB goes to A. Okay, again, 1A, 2 B's will be okay, and 3 B's will be BB, and BB goes to B again. So we will see these things. Now, let's focus on the changes for these things. When 2A goes to B, let's focus on only the actions. So our actions are these things. Okay, so we want to see these actions have what change in A and B. The first one, subtract A by 2 and add B by 1. This one, ABBA, number of A won't change, but number of B changes by 1. Here, number of B changes by 1. Okay, at 0. So as you can see, and in each step, number of A's will be decreased by number of letters will be decreased by 1. So we will reach one letter, and we want to see the last letter we reach is A or B. As you can see, number of A will be only subtracted by 2 if it is subtracted. If not, it won't change. So we can say parity of A is always same. So if we want to reach here A, so n of A in this case is 1. So if number of A is odd, we can reach A. If n of A is odd, we will reach a single one. If number of A is even, we will reach what? We will reach B. Okay, as you can see, number of A in all of them equal to odd number. Okay. It was invariant. You find what is constant. So which values of P and M resolve in a single A remaining at the end? We reached 1A if and only if number of A is odd. Okay. So we solve this problem completely by considering what in invariant and strings by parity. We have also some other things. You should define some functions. For example, we have some colorings in invariant. Colorings like what? Checkerboard scheme, which is so much useful also. We can use it in CSAT. And general formal checkerboard scheme. And it has type 1, type 2, and columns coloring. So if you learn invariant problems completely, invariant topics, and solve related problems, then we can solve problems like these that are useful. You also CSAT real problems. If you want to work more on invariant problems and want to solve problems, want to learn more ideas, as I said before, feel free to send message to my WhatsApp number in the description and comments. Okay, so let's focus on next idea. In this problem, again, we want to consider a small example and use the list copying rule. It says the function f is defined recursively for all integers n greater than 1 and p greater than 0. As follows, f of 1p is c plus p, f of n1 is c, f of np is f of n minus 1, and f of np minus 1, where c is greater than 0 is a real constant. Give a non-recursive expression for f of 4p. Proof is not required. Hint, you may want to try f2p. So look, it is a small example. Also, if we didn't have this hint, we could solve it with considering a small example. So let's see. It wants what? It wants f of 4p. So for finding f of 4p, we should use the third rule. F of 4p is what? Is f of 3 and f of 4p minus 1. So we understand that we need to find f of 3. For f of 3, we should find f of 2 and f of 1. So now we understand we should start from what? We know that f of 1p is what? Is c plus p. So f of 1p from first equation is okay. Let's focus on f of 2p. If you want to find f of 2p, we should use this part. And it will be what? It will be f of 1, f of 2p minus 1. So it is useful because p is greater than 0 if p is greater than 1. So if p is 1, f of 2, 1, it is what? It is c by second rule. And let's calculate f of 3, 1. F of 2, 2. By this rule, it will be what? It will be f of 1 and f of 2, 1. F of 2, 1 was c, so it will be f of 1 and c. F of 1 and c, if we use here, it will be what? It will be, look here, the intersection is what? When it is p1 and 1. So it will be what? It will be c plus 1. So let's say, n is greater than 1. This part, okay, so we can use it for n greater than 1, so they don't have intersection. So f of 1c is what? Is c plus c, which is 2c. So we guess that f of 2p is pc. So we can use it on by induction. We can want to prove that f of 2p equal to pc. So by a small example we found, and we want to generalize it, use induction. So by induction, we want to use from p minus 1 to p. F of 2p equal to what? Equal to f of 1 and f of 2p minus 1. So it will be what? F of 1 and p minus 1 times c. So we should use what? We should use first rule. It will be c plus second term. C plus p minus 1 times c, which is pc minus c plus c. It will be pc. Okay, so We found f of 2p or what? So f of 2p equal to pc. Now we should focus on finding f of 3p. So like here, again, we try to find, let me copy the rules. Okay, it says n greater than 1 because it is integer n at least 2, p greater than 0, p is at least 1. So for f of 3, 1 is what is c by using this? F of 3, 2. By using this part is f of 2 and f of 3, 1. It will be what? It will be f of 2 and c. 3, 1 is c. F of 2p is p times second term times c. Second term times c is c squared. Okay, f of 3, 3. If we use third rule, it is f of 2 and f of 3 and 2. It will be f of 2. F of 3, 2 is what? Is c squared. F of 2 and c squared by using this is second term times c. C squared times c, which is c cubed. So we guess what? We guess that f3p is what? Can you guess? It is c to the p. So let's use induction, p minus 1 to p. F of 3p equal to, by using third rule, equal to f of 2 times f of 3p minus 1. By induction, we can say it will be f of 2. F of 3p minus 1 is c to the p minus 1. And if we use this part, it will be what? It will be second term times c. So second term is cp minus 1 times c, which will be c to the p. Okay? So we've proved that f of 3p is c to the p. Now, last step, f of 4p is what? Again, like previous terms, first we focus on finding f of 4, 1. F of 4, 1, we use this, is what is c. F of 4, 2 is what? By using third rule, is f of 3 and f of 4, 1. So it will be what? F of 4, 1 is c, so it will be f of 3c. And if we use here, it is what? It is c to the power of second term. Here it will be c to the c. F of 4, 3 is what? It will be f of 3, f of 4, 2. It will be f of 3, and f of 4, 2 here is c to the c. And f of 3p is what? C to the second term. C to the power of, it's c, c. So 3 times we have. And we guess what here? F of 4p equal to what? Equal to c to the power of c to the power of c to the power of cp times. Again, we try to prove it by induction. P minus 1 to p. F of 4p equal to f of 3. You don't need to write, for example, f of all these one, all of them, only base case. We are writing to understand the solution. Some parts are for ourselves. F of 4p minus 1 by using third rule. Okay. Now that we've used third rule, f of 4p minus 1 by induction is what? We want to prove why it is correct. So we have c to the power of c, p minus 1 times. So it will be f of 3, c to the c to the c, p minus 1 times. And it is what? F of 3 and something is c to the power of second term. So it will be what? C to the power of second term. So because we have p minus 1 times p minus 1 c's here, so in general we have p times. We have pc's, okay? So we found f of 4p is what? And we proved by induction. So this strategy using considering small example telescoping rule, can say not. It is not so much related to telescoping rule. We could solve also by that, but most useful considering a small example and induction. Okay, this structure so much useful also in BMO problem, British Mathematical Olympiad, and also other exams. If you want to solve more problem with this idea that is related to real problems like CSAT that I saw, Feel free to send message to my WhatsApp number in the description and comments. Okay, so next idea, next problem. Okay, ideas in game strategies. I will tell you. Look, I can say 90% of the problem in game strategies can be solved with four ideas. The first one invariant. The second one is n and f of n. We have important idea here. And the next one symmetry can be useful. And last one going to the end of the game. And look, for example, the problem that can be solved with going to the end of the game cannot be solved with other problem. And with, for example, fourth idea, we can solve hard problems. And an f of n is so much useful. Also in this problem, useful in AMC problems, useful. So let's see there are what ideas. If you want to know all these four ideas and similar problem in CSAT and other exams, as I said before, feel free to send message to our WhatsApp number in the description and comments. Okay, let's read problem 18. It says let A, B, and C represent the number of tokens in three piles. A game between Alice and Bob starts with at most n tokens in each pile. A, B, C are greater than 0, less than or equal n, and consists of them taking turns. A turn consists of a player removing X tokens from one pile and Y tokens from a different pile with the constraint that X plus Y greater than 0. The player to remove the last set of tokens wins. Alice goes first in every game, and they play through all possible starting configurations of ABC, which are greater than 0, less than or equal to n. If Alice and Bob play in such a way that ensures their own number of wins is maximized, how many games does Alice win? Okay, so for solving this part, I want to use small examples, okay? So, I want to also solve when we have 0, okay? I don't count here, but they help us. So if we have, for example, f of, for example, a, b, 0, if you have 1, 0, which a and b are greater than 0, f means who is winner, first player or second player. Because it says we can select two pies and removing x tokens from one pie and y tokens from the other. So first player can remove all a tokens and b tokens here, and first player is winner. Because it says what? The player to remove the last set of tokens wins, okay? And if you have also, for example, f of a is 0, 0, again, if a is greater than 0, first player wins. Now let's focus on when they are not, when we don't have 0, for example, suppose when we have f of 1, 1, 1, okay? Who is winner? The first player can do what? Look from 1, 1, 1. First player can remove 1 from one of them, 1, 1, 0. Or look, it says x plus y greater than 0, so one of them can be 0. Or 1, 0, 0. And we know in both of them, second player is winner. So when first player goes to these things, so in 1, 1, 1, sorry. We prove that first player here is winner, first player here is winner. Okay, so when main first f here is 1, f here in this game 1. So the first player when goes to any of these two things will lose. Why? Because second player starts here and will win. So it will be what? It will be 2. So the lemma is what for n f of n? You are in position y. You have some choices. You can go to x1, you can go to x2, or you can go to xn. F of y is 1 if we can say, let me tell you, if there exists xi, that f of xi is 2. It is 2 if for all xi, f of xi is 1. It is so much useful. And we can solve hard problems, and it is useful in this CSAT problem, also useful in real CSAT problems I saw. So here, let's see. Here it is f1, it is f2. Now let's focus on, for example, f of 1, 1, 2. From 1, 1, 2, first player can go to what? 1, 1, 1. And because here f is 2, so first player goes here and he will win by this lemma. So here it is first player, f of 1, 2, 2. Again, it goes take 1 from each of them, 1, 1, 1, and because f of this is 2, it is 1. And f of 2, 2, 2. From 2, 2, 2, first player can take 1 from one of them. And we know if we change one of them to 0, for example, if 1, 0, we cannot change all of them to 0. 1, 0, and 2, 0, it will be f will be 1. So it is not good because we try to find one f that is 2. If we go, for example, to 2, 2, 1, it is not good because f of that is 1. If we go to 2, 1, 1, it is not good. If we go to 2, 2, for example, 0, it is not good. If we go to 2, 1, 0, it is not good because we have 0. If we go to 2, 0, 0, again, not good. All f's here are 1. Okay, so we understand f of that is 2. So if we were continue writing like this, we get something that if all three terms are equal, f is 2, otherwise f is 1. Claim. F of a, which a is greater than 0, is 2. And otherwise, f is what is 1. So let's prove it. For proving this, we use induction. Suppose we have a f of a, b, c. We use induction on what? We use induction on a plus b plus c. So if a plus b plus c equal to 1, it will be what? 1, 0, 0. And we proved when we have 0, it is 1, it is here. If a plus b plus c is 2, then we have two cases. F2, 0, 0 is 1. F of 1, 1, 0, also we proved this 1. A plus b plus c equal to 3, also we've considered. So if we consider it is f of 1, 1, 1, it is 2, we proved. And f of 3, 0, 0, we proved is 1. F of 2, 1, 0, also we proved is 1. And sum is 3, 3 ones, 3, 0, 0, 2, 1, 0. Okay. Now, let's open the page. Okay, so suppose from a plus b plus c to 1 to k minus 1 is okay. Now we want to prove for k. Case 1. If a equal to b equal to c, then it is a. So what are the cases? And we know a is greater. K is at least 4 because we proved for 3. So a is at least 1. A is at least not 1 because we've considered in base case a is at least 2. So a. We can select one of them, for example, a minus x, a minus y, and a, which x and y are greater than equal 0, x plus y. And because they are not, and some of the elements here is less than k, a plus minus x plus a minus y plus a is 3a minus x minus y, which is 3a minus k. Sorry. 3a here, sum of a. Length of a is k, so it will be k minus x minus y, which is less than k. Okay, so we can use induction, and f of that is 1 for all of them, because they are not equal, all of them. So here, by lemma, we proved f of a is 2. Lemma was what? Lemma was this. It was our lemma. Okay? Important lemma. Case 2. Suppose a and b and c are not equal. For example, a is not equal to b. At least two of them are not equal without loss of generality. Suppose these two things are not equal. So, we want to reach from A, B, C to a case that f is 2. We want to reach to two cases. So without loss of generality, we can consider A is less than B. Okay. Now, we consider a smallest one. Okay, maybe a smallest one is A or C. If A is less than or equal C, we consider A, we change B to A, how we subtract what? B minus A. And C to C minus A. Okay, and then it is what? It is equal to A, and f of that is 2, and it will be okay. If A is less than or equals C. If A is greater than C, so I move A to, because A is less than B, so we conclude in this case what? A greater than C, A less than B. We consider A minus C. And here the thing here we've subtracted is greater than 0. Here, for example, it is our x, our y. X plus y greater than 0 because B is greater than A. In this case, we subtract A minus C, and then what? B here, we consider B minus C and C. It is what? It is C, which f is 2, and by lemma, in both cases, we reach something that f is 2, so f of ABC in this case is 1. So we proved our claim. Now we can solve the problem easily. So it says, in how many of them who wins Alice win? Who starts Alice and Bob play? Okay, a game between these turns. A turn consists of this with the constraint. The player removed. Alice goes first. Okay, so if you want to find the answer, Alice wins first player when they are not equal. So ABC are from 1 to n. So it will be n cubed minus the cases that they are equal. All of them 1, all of them 2, all of them 3, all of them n. So in this number of cases, Alice wins. Okay, so we solved this problem by using n and f of n. I told you this. If you want to see how you can solve other problems, for example, AMC problems with some problems are a combination of two of them. For example, one AMC problem is combination of n, f of n, and symmetry. If you want to learn other ideas on how to approach the problems of CSAT related to game strategies, as I said before, feel free to send message to my WhatsApp number in the description and comments. And if you want to work on ideas related to real problems of CSAT and sample problems, you can send message. Okay. This one, composition of functions we have, and probability in dice game. Okay, let's focus on this. Okay. Problem 2, let f of x mean that function f is applied to x, and f n of x means if you take f from x n times, that is f is applied to x n times. Let g of x equal to x plus 1, h n of x equal to g n of x, and what is h n of m of 0? Okay. So first, when we have this h n of m of 0, if we use the definition, it will be what? h n of 0. How many times? M times. Okay, so first we should calculate hn of 0. Hn of 0 is what? It's gn of x. So it means what? G of x. How many times? N times. Okay, so let's see here how can we calculate g of x. Again, you use a small example. G of x is x plus 1. G of x is what? Is g of x plus 1. So it is x plus 1 plus 1, x plus 2. So g2 of x is this. And we guess that gn of x equal to what? Equal to x plus n. How we can prove it? By induction. From n minus 1 to n. We want to prove it. Gn of x equal to g of gn minus 1 of x. So it will be g of, by induction, we can say it is x plus n minus 1. And then you add 1 again. It will be x plus n minus 1 plus 1. Which is x plus n. Okay? So we proved gn of x is this. Now, so hn of 0 is, here x is 0, 0 plus n, which will be n. So hn of 0 is hn of 0 is n, but hn of x equal to gn of x, which we proved it is x plus n. Okay. Now again for this one, for hn, we use again a small examples. Hn of x equal to x plus n. Now hn of 2 of x equal to hn of x. It will be hn of x plus n. We add n again, it will be x plus n, which is x plus 2n. Hn of 3 of x equal to hn of 2 of x, which will be what? Hn of x plus 2n. And here it will be x plus 2n because of definition of hn plus n, x plus 3n. So we can guess that hn of m of x is what? M of x is x plus mn. How we can prove it? By induction on m minus 1 to m. So hn of m of x equal to hn of m minus 1 of x. So it will be hn of x plus m minus 1 times n. And by definition of hn, it will be x plus m minus 1 times n plus n. So it will be what? It will be x plus mn minus n plus n. It will be cancelled, so it will be x plus mn. So we proved that the answer is x plus mn, but because it says 0, so it is 0, so we can say hn of m of 0 equal to mn. It is our answer. Okay. So here, look, the idea was what, using a small examples that is so much useful in CSAT problems. There are some ways, some approaches that is so much useful in CSAT problems, real CSAT problems, sample problems, other exams like AMC, BMO. If you want to learn those important approaches, as I said before, feel free to send message to my WhatsApp number in the description comments. Okay. The last problem, last idea that we want to consider in this video. In CSAT 2023 interviews, something like that, 2022, we had in real CSAT, we had a problem related to probability in dice game. I can't tell you that problem, but we can solve because there are lots of problems related to probability in dice game. We can solve an AMC problem related to that for American mathematics competition. To see, there are also lots of other problems, and we should solve many problems related to that to get good at these types of problems. It says what Kyla rolls 4 fair 6-sided dice. What's the probability that at least one of the numbers Kyla rolls is greater than 4 and at least 2 of the numbers she rolls are greater than 2? Okay, so we know that when a number is greater than 4, it is also greater than 2. So we can say what? One of them should be greater than 4, and one of the numbers should be greater than 2, like this. Okay, now we want to consider bad cases, okay? It is easier to work on bad cases. It has many solutions. One bad case is we have one greater than 4, but the others are at most 2. Okay? It means first condition is satisfied. Now, if first condition is not satisfied, it means all of them are less than or equal to 4. And as you can see, these two cases don't have intersection. So all we want to find good cases, the probability that we want to find, probability, good cases over all cases here. And good cases equal to what? We can say 1 minus bad cases, because all cases minus bad cases, all over all will be 1. Bad cases over all cases, okay? Now it will be what? 1 minus bad, all cases is what? We have 4 four-sided dice, so each of them has 6 choices, 6 to the 4. Now, let's consider these bad cases. The first one of them is greater than 4, so 4 choose 1. That one can be 5 or 6 times 2. And the other one can be only 1 and 2, so 2 cubed. Plus the other bad case, all of them are from 1 to 4, so it will be 4 to the 6. Okay? So, sorry, 4 to the 4. because we have 4 dice. So it will be what? 1 minus 4. This one is what? 2 times 2 cubed is 16. 4 times 16 is 64. Plus 4 to the 4 is 2 to the 8, which is 256 over 6 to the 4. Before calculating this, I can divide by 2 to the 4, both numerator and denominator. So 2 to the 4 means 16. It will be 4, and 2 to the 4 for next one is 16. So it will be 1 minus 20 over 81. 81 minus 20 is 61 over 81. It is our answer, and the solution is 61 over 81. Here we had 4 dice. In some problems we have 2 dice. And we have many different probabilities in dice game. If you want to learn other problems in probability in dice game, want to work on more ideas that are in real CSAT problems that I saw, in interviews, many other parts in official exams. If you want to learn those ideas, want to solve more problems, if you want to prepare for CSAT or other exams, as I said before, for applying Cambridge, Stanford, top universities, if you want to prepare for Olympiad exams, AMC, AME, USAMO, BMO, UKMT Senior, Junior, Intermediate, BMO2, many other exams. Feel free to send message to my WhatsApp number in the description and comments. And as I said before, there are 40, 50 important ideas in each topics: geometry, combinatorics, algebra, number theory. If you want to learn them, you can send message to my WhatsApp number. Thanks for watching this video. Have a great day. Bye.